So uh, imagine you're standing in front of your 8 a.m. general chemistry
Oh,
class.
early.
Right, very early.
Mhm.
And you tell them that the clear plastic wrap they literally just used on their sandwich could theoretically anyway be engineered to conduct electricity.
Which just sounds completely made up to them.
Exactly. Or like you tell them if they take everyday carbon atoms and arrange them perfectly, they don't get a diamond. They get a microscopic molecule shaped exactly like a soccer ball.
I mean, that completely shatters that whole assumption that chemistry is just, memorizing rules for some isolated reaction in a beaker.
Right.
You're introducing them to this world where materials just kind of bend the rules of physics.
Which is exactly why we are dedicating today's deep dive directly to you, our listener, because we know you're a community college chemistry professor out in Oregon, and you're currently prepping to teach Chapter 24.
Right, the modern materials chapter.
Yep, from Julia Burge's Chemistry, Atoms First.
And our role today is really just to act as your specialized deep dive assistants. So we've analyzed the textbook chapter and your lecture slides to help you map out this specific segment of your paced fall, winter, and spring curriculum.
Right.
The whole goal is to isolate those foundational teaching strategies, anticipate the specific misconceptions your students are definitely going to face, and build out those crucial aha moments.
Because, I mean, at the community college level, the challenge isn't just delivering the content, it's making it accessible, right? You want to hook them with these real-world applications before you ever hit them with the really complex calculations. So let's just jump in. The text anchors this entire chapter on polymers, which, makes sense.
They are everywhere.
Literally everywhere. But to understand these massive engineered materials, we first have to, figure out how they are built from simple monomer units.
Yeah, and the foundational concept here is addition polymerization. So the textbook uses the synthesis of polyethylene from ethylene or ethene as the starting point. And the underlying mechanism there is really all about electron movement. You start with an alkene, right? A molecule with a carbon-carbon double bond, and you introduce an initiator molecule to basically get the chain reaction going.
And see, this is where I can see students just immediately getting lost. Because the text talks about a free radical initiator. And, I mean, for a student who just got comfortable with stable octets, a free radical sounds terrifying.
Yeah, it sounds chaotic.
Yeah. So how do we explain the mechanics of a free radical without, losing the room? Could you frame it as something like an energetic home wrecker?
A home wrecker.
I like that. It's got this single unpaired electron, so it's just desperately seeking stability. And it crashes into the ethylene molecule and physically snaps that double pi bond in half just to steal an electron.
Let's refine that just slightly to make the chemistry crystal clear for them. It doesn't just steal an electron, it forces a total reorganization.
Okay.
That unpaired electron on the radical forms a new single covalent bond with one of the electrons from the pi bond.
Right, right.
And that leaves the other electron from the pi bond just kind of orphaned on the far carbon atom. So now that entire molecule is a radical. It becomes the new home wrecker, seeking out the next ethylene molecule.
Oh, I see. So the reactivity is just transferred down the line, monomer by monomer, basically zipping together this massive chain.
Exactly.
And there's a specific visual cue in the text for this, isn't there? Figure 24.1 shows reaction arrows, but they look weird. They only have half a pointed head.
Right. Those are fishhook arrows, and you should definitely point those out in your lecture slides because a standard full-headed arrow shows the movement of an electron pair.
Okay.
But a fishhook arrow tracks the movement of a single electron. It visually reinforces that this entire chain reaction is driven by solitary electrons just searching for a partner.
I love that. Okay. So the electrons move, the monomers link up, and we get a massive chain of polyethylene. But looking at the textbook drawings, I spot a massive trap for a student.
Oh, the 2D representation.
Yes. The polyethylene chain is drawn horizontally across the page as this perfectly straight, flat, rigid line of carbon atoms. If I'm a student looking at that, I'm assuming plastic is microscopic rebar.
Yeah, that is a primary misconception you have to intercept right away. Students trust 2D drawings implicitly.
So true.
So this is the perfect moment to pause the lecture and force them to recall Chapter 7. Have them look at any central carbon atom in that drawn chain. It is surrounded by 4 single bonds. What does VSEPR theory, valence shell electron pair repulsion theory, tell us about a central atom with 4 electron domains?
Oh, right. Those domains repel each other maximally in three-dimensional space. So they weren't just sitting at 90-degree or 180-degree angles. They push into that tetrahedral geometry, which is approximately 109.5 degrees.
Therefore, the carbon backbone cannot physically be a straight line.
Why?
It is a continuous three-dimensional zigzag. Furthermore, because these are all single sigma bonds, the atoms can freely rotate around the bond axis. So the polymer chain can twist and coil and fold back on itself like a bowl of microscopic spaghetti.
Which completely explains the macroscopic properties. Like, it's flexible because the microscopic chain is a rotating zigzag, not a rigid rod. That is a fantastic aha moment.
It really connects the micro to the macro.
Wait, if they're all just twisting chains of polyethylene, why does a plastic milk jug feel completely different from, say, a flimsy plastic sandwich bag? I mean, they're made of the exact same monomer.
So this comes down to the reaction conditions during synthesis, which can actually cause branching. Imagine a long chain of carbon atoms, but occasionally a side chain of carbons just shoots off the main backbone.
Okay, let me try to visualize the impact of that. If the chains are largely unbranched, they're smooth. They can pack together very tightly, laying parallel to one another.
Exactly.
Kind of like packing straight, uncooked spaghetti noodles perfectly into a box. And that dense packing creates high-density polyethylene, or HDPE. That's the rigid milk jug.
Yes. That tight packing maximizes the intermolecular forces, specifically the dispersion forces between the chains, which makes the material strong and rigid.
Okay, makes sense.
But if your reaction conditions encourage a lot of those side branches to form, the chains physically cannot get close to one another. The branches act like molecular elbows, basically pushing neighboring chains away.
So it's like trying to pack a box with tree branches instead of spaghetti. There's so much empty space.
Right. And that empty space lowers the overall density, which gives you low-density polyethylene, or LDPE. The weaker intermolecular forces mean the material is highly flexible and softer.
Wow.
It's the exact same chemical formula, but a slight change in the microscopic geometry completely alters the physical world application.
I just love how physical this all is. And if you want to keep the class hooked on those physical applications, especially, the sports fans in your room, you can pivot from plastic to rubber. Vulcanization.
A classic.
Yeah, the text mentions that natural rubber is an addition polymer of isoprene, but on its own, it's not very useful for a car tire, is it?
Not at all. Natural rubber is an elastomer, so the coiled chains can stretch out when pulled and snap back when released. But if it gets too hot, it just melts into a sticky mess.
Gross.
And if it gets cold, it becomes brittle. It lacks structural integrity because the separate polymer chains can slip past each other way too easily under stress.
Entered Charles Goodyear in the 1830s. He figures out that if you heat this natural rubber with sulfur, it changes everything. But what is the sulfur actually doing on a molecular level?
So the sulfur atoms undergo a chemical reaction where they form covalent bridges, what we call crosslinks, between the adjacent polyisoprene chains.
Wow.
Instead of independent chains slipping past one another, you now have a massive interconnected three-dimensional network. The chains can still uncoil and stretch, but those sulfur bridges act as anchors, preventing them from sliding apart permanently.
And this is where you drop the real-world NASCAR hook in your lecture. Because tire manufacturers can control the exact amount of sulfur cross-linking, they can tune the rubber's properties on demand.
No, absolutely.
Like, in a 500-mile race, a single car might burn through 32 tires, costing $400 each. Teams will literally use different sulfur-tuned rubber compositions on the left and right sides of the car to handle the specific banking of a track.
That's crazy.
Less sulfur means a softer tire that grips the asphalt like glue but shreds really quickly. More sulfur creates a harder, durable tire with less grip. It is all dictated by the number of sulfur bridges.
It's basically applied chemistry at 200 miles per hour.
Totally.
And, before you move on to the next major topic, you'll need to contrast these addition polymers with condensation polymers. It's a subtle but really vital distinction.
Right, because with an addition polymer like polyethylene, every single atom from the ethylene monomers ends up in the final plastic. Nothing is lost.
But in a condensation polymer like nylon, or the proteins forming in our own bodies, the monomers typically have two different functional groups. When they react to link together, they actually have to eject a small piece of themselves to make the connection.
They kick out a small molecule, usually water, right? Like an amino group reacting with a carboxylic acid group. They bond, But a water molecule is eliminated as a byproduct. Condensation.
Exactly. That elimination is the defining characteristic your students need to look for when classifying the reaction.
So at this point in the term, you've established the rules. Your students understand that polymers are massive, covalently bonded insulators. Their electrons are locked down tightly in sigma bonds. But, a great lecture thrives on subverting expectations.
Oh, definitely.
You put a piece of plastic wrap on the projector and ask, can this conduct electricity?
And every instinct they have developed so far should scream no. Conductivity requires mobile charge carriers, like the sea of electrons in a metal wire.
Exactly. It seems impossible. But then you introduce polyacetylene. And here's a spot in the textbook that will absolutely trip them up if you don't catch it. Common name is acetylene. That -line suffix makes it sound like an alkene.
Yeah, it's a very frustrating quirk of historical naming conventions. The systematic name is ethene. It is an alkyne, meaning the two carbon atoms are joined by a triple bond, not a double bond.
Wait, okay, let me play the role of the confused student here. If we use a free radical initiator on a triple bond, doesn't it just break the bonds down until we are left with a single bonded polymer chain, just like we did with ethylene? Why would it be any different?
That is the logical assumption. But here is the mechanism. The initiator only has the energy to break one of the pi bonds in that triple bond to form the links to the next monomer.
Why?
The second pi bond remains completely intact. So when the chain zips together, you aren't left with a backbone of purely single bonds. You are left with a chain that has alternating double and single carbon-carbon bonds.
Okay, alternating double bonds. But why does that magically turn a plastic into a conductor?
Think back to the shapes of the orbitals. In a standard plastic like Teflon, all the valence electrons are trapped in localized sigma bonds between the atoms. But in polyacetylene, every single carbon atom in the chain still has an unhybridized orbital sticking up perpendicularly, holding that remaining pi bond electron. Because these double bonds alternate down the entire chain, all those orbitals overlap with one another.
They create a continuous overlapping highway.
Precisely. The electrons are no longer localized to one specific bond. They become delocalized across the entire polymer chain. So if you apply an electric potential, those delocalized electrons can flow freely down the orbital highway. You have literally engineered a plastic wire.
That is brilliant.
No.
You just fundamentally changed their understanding of organic chemistry.
Yeah.
But manipulating the electrical properties of organic molecules isn't just about making wires. It's also about how we interact with technology visually. Which brings us to liquid crystals.
Yes.
When your students hear liquid and crystal, those seem like mutually exclusive phase states.
It is a total paradox to them. The best way to clarify it is to focus on two distinct concepts: isotropic versus anisotropic materials.
Let's break those down.
Sure. Take a glass of standard liquid water. It is isotropic. The molecules are tumbling randomly in all directions.
Okay.
Because of that chaos, the physical properties of the water, like how it bends light, are identical no matter which angle you measure from. But a crystal, like a diamond, is anisotropic. Its atoms are locked into a rigid, highly ordered grid. So its optical properties change drastically depending on the angle the light hits the crystal face.
So a liquid crystal is somehow both.
Yes. The molecules in a liquid crystal flow and pour like a liquid, but they are long and rod-shaped, and they tend to align parallel to one another. They actually have a degree of structural order.
The text mentions 3 types of alignment: nematic, smectic, and cholesteric. What do those actually mean for a student trying to visualize this?
Think of the rod-shaped molecules like matches in a box. In the nematic phase, all the matches are pointing in the same general direction, but their ends don't line up perfectly. They are staggered. In the smectic phase, they point in the same direction, and they organize into distinct parallel layers. And the cholesteric phase is like a spiral staircase, where each layer of molecules is twisted slightly relative to the one below it.
Okay, the structure makes sense, but the application is what will cement this in their minds. The liquid crystal display, the LCD, there's a diagram in the textbook figure 24.11 that shows how a digital watch face works.
Right. In an LCD, a thin layer of these nematic liquid crystals is sandwiched between two polarized glass filters. Normally, the liquid crystals are twisted in a way that guides the light through both filters so the screen looks blank or, bright.
But when you press a button on the watch and an electrical current is applied,
the current creates an electric field. Remember, these molecules are highly polarizable. The electric field forces the rod-like molecules to snap to attention and align themselves with the field.
Wow.
When they align, they stop guiding the light. The polarized light is suddenly blocked by the second filter.
Which creates a dark spot on the screen. You are literally watching microscopic molecules stand at attention to form the number 8 on your calculator. And when the current drops, they relax, the light passes through, and the number vanishes.
It is just a stunning example of controlling molecular geometry with electricity.
It really is.
Yeah.
So we've seen how we can engineer polymers and crystals to manipulate light and electricity. But it's one thing to put these materials in a digital watch. It's an entirely different challenge to put them inside a human body.
Oh, absolutely.
When you introduce a synthetic polymer or a metal into living tissue for like a joint replacement or a dental implant, the immune system doesn't care about its electrical properties. It just sees a foreign invader.
The biological hurdle is immense. The immune system's primary job is to recognize non-self materials and attack or encapsulate them. So the textbook points out that the true challenge of biomaterials isn't just mechanical strength, it's biocompatibility.
Right.
You have to design a surface chemistry that tricks the body into thinking the implant actually belongs there.
Let's focus on ceramics for a moment, because if you are replacing the bearing of a hip joint, you need something incredibly hard, wear-resistant, and chemically inert. Ceramics are perfect for that. But traditional ceramics are made by mixing dry powders and firing them in a kiln.
Yeah, the old school way.
Right. If you try to make a hip joint that way, wouldn't the microscopic gaps between the powder grains create weak points? You can't have a hip joint shatter when someone jumps.
You absolutely cannot have voids. That is why modern biomedical ceramics often use the Sol-Gel process. Instead of starting with dry, clunky powders, chemists start with a solution, a liquid solvent like methanol. They dissolve the precursor chemicals in the liquid.
Oh, because it's a liquid solution, the mixing is happening at the atomic level, not just the granular level.
Correct. Through chemical reactions in the solution, they form a sol, which is a suspension of perfectly uniform microscopic particles of amorphous silica. They can control the size of these spheres down to the nanometer.
Incredible.
They then induce these spheres to link together into a gel, which is a continuous three-dimensional network.
So you've got this gel of perfect spheres. But it's still not a solid ceramic hip joint. How do you solidify it without creating those dangerous gaps?
The text mentions sintering. Is sintering kind of like, okay, think about when you pack a snowball with your bare hands.
Okay, I'm tracking.
You start with loose flakes of snow, which are your uniform silica particles. But if you just pile them up, they crumble. So you apply pressure and the heat from your hands. You don't melt the whole snowball into a puddle, but you melt the very outer edges of the flakes just enough so they freeze together into a solid, gapeless block of ice.
That is a phenomenal macroscopic analogy.
Yes.
Sintering is essentially solid-state diffusion. You heat the ceramic material to a temperature just below its melting point. The atoms on the surface of these microscopic spheres become highly energetic.
Okay.
To reduce their overall surface energy, the atoms migrate across the boundaries where the spheres touch, physically fusing them together.
So the pores literally vanish as the material densifies into one continuous, unbreakable matrix. Exactly. You eliminate the microscopic pores that would otherwise act as stress concentrators where cracks could begin.
That's amazing. Now, to ensure those ceramic spheres have no gaps, or to confirm the alignment of liquid crystals, we have to look closer than a traditional light microscope allows. I mean, a light microscope is limited by the wavelength of visible light. To manipulate modern materials, we really have to enter the nanorealm. We need to see the atoms themselves.
And this requires a massive shift in how students think about seeing. The text highlights two revolutionary tools: the scanning tunneling microscope, the STM, and the atomic force microscope, the AFM.
Let's start with the STM. The word tunneling sounds like science fiction. What is actually happening?
Well, it relies on quantum mechanics. You bring an incredibly sharp metal tip, sometimes ending in literally just a single atom fractions of a nanometer away from the surface of your sample.
But they're not touching.
No, they are not touching. There is a vacuum gap. In classical physics, an electron cannot cross that empty space. But in quantum mechanics, the electron acts as a wave. It has a tiny, measurable probability of simply tunneling through the barrier and appearing on the other side.
So by applying a small voltage, you get a measurable current of electrons just tunneling across the gap.
Yes, and that current is exponentially sensitive to the distance. If the tip moves closer to an atom on the surface by even a fraction of an angstrom, the current spikes. The computer monitors this current and moves the tip up and down to keep the current perfectly constant as it scans across the surface.
Oh, wow.
By recording those up and down movements, it actually maps the electron clouds of the individual atoms.
But there is a huge catch here, right? If you need a current to flow, the sample has to be electrically conductive. You couldn't use an STM to look at an insulating piece of polyethylene or biological cell.
Exactly. That is the STM's major limitation, and that is why the atomic force microscope, the AFM, was invented. It solves that problem by taking electricity out of the equation entirely.
How does the AFM map a surface if it isn't using electrons?
It relies on physical touch, or rather the physical forces of attraction and repulsion. The AFM uses a microscopic stylus attached to a flexible cantilever, much like a needle on a record player. As this stylus is dragged over the atomic peaks and valleys of the sample, the intermolecular forces between the atoms push and pull the cantilever up and down.
But those movements must be impossibly small. How does the machine measure a cantilever bending by, like, a nanometer?
It's pretty clever. They bounce a laser beam off the shiny back of the cantilever onto a highly sensitive photodetector. Even the most microscopic bend in the cantilever causes the reflected laser beam to deflect significantly across the detector.
Oh, that makes sense.
Right, it translates intermolecular forces into a 3D topographic map. And because it relies on physical forces, not electrical current, an AFM can map anything: insulators, ceramics, even living DNA molecules.
And when we use these incredible tools to look closely at carbon, we discover some wild things. Your students know the standard allotropes of carbon. They know diamond, where carbon is St3 hybridized, locked in a rigid 3D lattice. It's an insulator.
Right, and they know graphite, where the carbon atoms are sp2 hybridized, forming flat hexagonal sheets.
Oh, wait, let me pause on graphite. Earlier we talked about polyacetylene conducting electricity because of unhybridized p orbitals. Does graphite conduct electricity for the same reason?
Yes, it's the exact same mechanism. In those flat graphite sheets, every carbon atom has an unhybridized p orbital pointing perpendicular to the layer.
Okay.
Those orbitals overlap, creating a massive delocalized network. Electrons can flow freely across the entire sheet, which is exactly why graphite is highly conductive while diamond is not.
So we have the rigid 3D lattice and the flat conductive sheets. But in 1985, scientists vaporized graphite rods with intense laser light in a helium atmosphere, and the resulting soot contained an entirely new allotrope, C60, the fullerenes, or, buckyballs.
The geometry of C60 is what makes it so breathtaking. When the vaporized carbon atoms recombine, they don't form flat sheets. 60 carbon atoms arrange themselves into a closed hollow cage. Mathematically, it is a truncated icosahedron.
Which, if you tell your students, is literally the exact geometric pattern of a standard soccer ball. It consists of 12 pentagonal faces and 20 hexagonal faces. It is perfectly symmetrical.
It really is.
It just goes to show how immensely versatile a single element can be based purely on how its atoms are connected.
And manipulating how elements connect is the perfect transition to the final, most impactful topic for a modern materials lecture: semiconductors. I mean, this is the bedrock of the entire digital age. Your phone, your computer, the solar panels on a roof, they all rely on semiconductors.
But teaching semiconductor physics can get incredibly dense with quantum mechanics. How do you introduce this to a community college student in a way that is highly predictive and intuitive?
The textbook offers a wonderfully elegant shortcut for predicting semiconductor combinations: the magic number 8 rule.
Okay, the magic number 8.
You simply have your students pull out their periodic tables. If you are combining main group elements to make a binary semiconductor, you just look at their group numbers.
Because the group number corresponds directly to the number of valence electrons.
Exactly. If the sum of the valence electrons from the two elements equals 8, that combination has a very high probability of forming a functioning semiconductor.
Let's test that. So indium is in group 3A, so it brings 3 valence electrons. Phosphorus is in group 5A, bringing 5. 3 plus 5 is 8. So indium phosphide should be a semiconductor.
It is, and a very important one for high-speed electronics.
That is a great trick for a multiple-choice exam. But you still have to explain why the number 8 matters. Like, what is actually happening to the energy of these electrons?
Well, to explain the why, you have to introduce the concept of energy bands. Imagine two distinct energy levels. The lower level is the valence band. This is where the electrons normally reside, locked into their covalent bonds. The higher energy level is the conduction band. It is mostly empty, but if electrons can reach it, they can move freely and carry a current.
So the ability to conduct electricity depends entirely on the gap between these two bands.
Yes. In a metal, a conductor, there is no gap. The valence and conduction bands overlap. Electrons flow without any barrier.
Got it.
In an insulator, like rubber, the energy gap between the bands is massive. The electrons simply do not have enough energy to jump the chasm.
So a semiconductor must sit right in the middle.
It sits perfectly in the sweet spot. A semiconductor has a small, distinct energy gap. At absolute zero, it acts like an insulator. But at room temperature, the ambient thermal energy is just enough to excite a small fraction of the electrons across the gap into the conduction band.
So by combining elements that sum to 8 valence electrons, you are ensuring an average of 4 valence electrons per atom. You are perfectly mimicking the tetrahedral covalent bonding structure of silicon or germanium, which establishes that exact, narrowly tuned energy gap.
Exactly. You are engineering the exact conditions needed for controlled conductivity.
It is the ultimate expression of structure dictating function.
It really is.
Which brings us to the ultimate visual showstopper to close out your lecture. If you want to leave your students wide-eyed, you end with superconductors.
Oh, always a crowd pleaser. A superconductor is a material that, when cooled below a certain critical temperature, loses all electrical resistance.
All of it.
All of it. The electrons pair up, known as Cooper pairs, and move through the atomic lattice without any scattering or energy loss whatsoever.
But you can't see zero resistance, so you show them figure 24.2. It's a photograph of a small black ceramic pellet, specifically a YBCO ceramic. It is sitting in a dish of liquid nitrogen, cooling it to a blistering negative 196 degrees Celsius.
Very cold.
Right. And hovering above the ceramic pellet, levitating completely unsupported in midair, is a permanent magnet.
This is the Meissner effect. As the ceramic crosses its critical temperature and becomes a superconductor, it does something extraordinary. It actively expels all magnetic fields from its interior.
But why does that make a magnet float?
Well, when you try to bring a magnet close to the superconductor generates surface electrical currents that create an opposing magnetic field. It basically acts as a perfect magnetic mirror.
Oh.
The expelled field of the superconductor physically pushes back against the field of the falling magnet with identical force, locking the magnet in levitation.
It looks like pure magic, but it is entirely chemistry. It's the result of manipulating atoms so precisely that they rewrite the rules of electromagnetism. In fact, discovering this property in ceramics won J. Georg Bednorz and K. Alex Muller the Nobel Prize in Physics in 1987.
It definitely proves to your students that chemistry is far from a finished science.
So let's look at the incredible journey you've just mapped out for your classroom. You start by untangling the zigzagging VSER geometry of polyethylene to show how branching changes a rigid milk jug into a flexible bag. You capture their attention with Charles Goodyear, sulfur crosslinks, and NASCAR tires.
Then you force them to rethink insulators by explaining how alternating double bonds create highways for delocalized electrons in conducting plastics. You explain how liquid crystals align under an electric field to block light in their watches.
You navigate the biomedical challenges of the immune system by explaining how the Sol-Gel process and sintering eliminate microscopic pores to build unbreakable ceramic hip joints.
And finally, you give them the tools to see the invisible, the quantum tunneling of an STM, and the physical touch of an AFM. You show them carbon molecules shaped like soccer balls, predict semiconductors with the magic number 8, and literally levitate magnets.
It is a phenomenal amount of material to cover across a term. But by anchoring these concepts in physical mechanisms, focusing on the why, instead of just you're taking these dense, high-level ideas and translating them into foundational atoms-first stepping stones for your Oregon Community College students.
You are giving them the tools to look at the physical world and see the atomic architecture underneath.
And as a final thought to leave lingering in their minds, no, let me rephrase. We've seen how rearranging the exact same carbon atoms can yield the graphite in their pencil lead, a brilliant diamond, or an electrically conductive microscopic soccer ball.
Right.
If structure so completely dictates function, what happens when artificial intelligence allows us to computationally predict and assemble entirely new, highly strained geometries of everyday atoms that the universe has never naturally produced? What seemingly impossible material properties might your students be the ones to discover?
That is exactly the kind of question that creates future chemists.
Good luck teaching Chapter 24.